Could there be a smallest possible distance? We can take a foot and chop it into 6 inches. We can take 6 inches and chop it into 3 inches. And we can continue doing this as far as we want. Can we continue to chop up distances forever until they're infinitely small? Well, the answer seems to be no. And it's crazy to me that you can't continually do this forever. It kind of makes sense that you would always be able to chop it in half. But if you think about a stack of Legos, there's a finite number of Legos, and we can chop the Lego stack in half continually, just like with a measurement, until eventually we get down to one single Lego. After we get down to one Lego, there's nothing else we can do. We've chopped it up as far as possible. That's what distance is. But you can imagine something similar with energy. If you're looking at the battery on your phone, there's a percentage, up to 100%. And once you get down to 1%, everything below that is pretty much zero. So if your phone battery has percentages, let's say after using our phone for 5 minutes, 1% is used up. Just like the Lego and the percentage of your battery, there are actual quantities of length and energy at which you can't divide them up anymore. They're a single value or a single quantity. The way this actually came about was in the early 1900s. Scientists were studying how black bodies emit light when they're heated up. All forms of matter emit some kind of electromagnetic radiation, and the greater you heat them, the more light they emit. You can think of an eye on your stovetop turning red. So the temperature of the matter affects what color light is emitted from the atoms and the electrons. And when scientists were studying this in the early 1900s, they measured different curves of light that corresponded to temperature. And they were trying to predict or create a model that would measure the light curves that they saw coming out of these black bodies. This is actually how quantum measurements began. And one of the first quantum values that was discovered was by Max Planck. And he discovered that there was an actual quantity of energy at which point it couldn't be divided anymore, just like the Legos. This quantity is called Planck's constant, and it's a proportion to the frequency of light emitted. As the light emitted from a heated object changes color, it goes from red to blue, that frequency can be multiplied by a finite value that's constant to get the amount of energy that's being released in terms of light. And this proportion between the frequency and the energy, which is a constant value, actually didn't make sense at the time. What this means is that the constant is like the Legos. Can't be divided up any smaller, and it never changes, just like the length of the Lego. And if you want to measure some energy using the frequency of the light, you have to multiply it by this constant value. So that means that the energy being emitted from a black body radiating photons is actually comprised of a bunch of tiny little pieces. So how does a quantity or a finite amount of energy lead to a finite length that can't be divided up any smaller? Well, as it turns out, every measurement has some kind of unit. So we can measure length, time, speed, acceleration, etc., mass, all of these types of things. And by combining them in different ways, we can get certain values out. So if you imagine a speed, 30 miles per hour, and if you want to get an amount of distance that you've traveled, you can multiply it by a time. So your speed is a distance over time, and you can multiply by the amount of time that you've traveled. And so the time on the top and the time on the bottom cancel out, and you're left with a distance. So this canceling of units is actually something called dimensional analysis. And it's simply taking the units of different measurements and different values and combining them in certain ways to get what you want out, just like we did with meters. And using Planck's constant, which has certain units associated with it, and using two other fundamental constants of nature, the gravitational constant and the speed of light, we can combine them in a special way to get out a distance or a time. And this distance and time are universal values. They are made up of constants that come to us from the universe. The gravitational constant doesn't change, and it's represented in the force of gravity. The speed of light obviously is a constant of nature and doesn't change no matter where you go, at least we think. And Planck's constant is represented in all kinds of quantum calculations. So not only is it the proportion of a subatomic particle's frequency to its energy, but it's represented in all kinds of quantum equations. So if we look at dimensional analysis on paper, it's really nothing crazy. Like I said, distance over time multiplied by time gives you distance. So if we involve just a few more variables, we can get the three constants that we've been given by the universe, essentially, and combine them to get a distance or a time. Let's start with the force of gravity. So the force of gravity is measured in newtons, but the equation for gravity is one way to calculate force between two bodies of mass, but we can also use force calculated by ma, and that just is mass times acceleration. So the units for this are obviously mass. We'll use m for mass, and a acceleration has subunits. So acceleration is just meters per second per second. So we've got a distance over a time squared, because we have the amount your distance changes per second every second. So your velocity, in other words, changing over time. So the units for force are mass times distance over time squared. Another way to think about this is if we have a 1 kilogram block and we apply force to it, which is equal to distance over time squared. So if we want to push this block, we obviously have to apply a force. And you can imagine something moving through space. Let's say there's no friction. It's going to continue moving forever at the same speed. But if we want to speed it up or slow it down, that takes extra force. And that force is because of the acceleration. We're either speeding it up or slowing it down. So we're changing its velocity, and that requires us to apply some force to it. So if we wanted to calculate the force of gravity between two bodies of mass, we would say F equals mass 1 times mass 2 over the distance squared times g, which is our gravitational constant that we mentioned earlier. So these two masses could be planets, could be an apple and a human, could be anything. And their distance affects their force of gravity. So you can imagine as two things get farther away, their force of gravity decreases, which is why we're dividing by the distance. And it specifically decreases with the square of the distance. So if you're twice as far away, the distance is 4 times as small. And similarly, if you're twice as close, the force is 4 times as great. And we've already said that the units for force are mass times distance over time squared. If we multiply everything on the right side of the equation here, we must get these units out. So we've got mass squared, because it's a mass times another mass, over a distance squared. So what we're left with is a mass and a distance cubed, and we also need a time squared. So if we take the dimensions and cancel them out, we'll end up getting what's on the left side here. So 2 m's divided by 1 m, the m's cancel out and we get 1 m left on the top. So that gives us 1 m on the top, just like we have on the left side. And then 3 d's over 2 d's Two of those d's cancel out, and we're left with one d on the top, just like on the left side. And then we have only time left. So we've got time squared left. So now our units match up. They're the same on both sides. So we know that by taking mass 1 times mass 2 over distance squared times some constant value gives us our force between the two bodies of mass. And we know because of the units of this portion of the formula that the units of g must be this, which is d cubed over mt squared. So that's what the units of g must be in order for this formula to actually give us a force out in terms of the units. These units of g don't actually have to mean anything, we just need them to match up so that we get what we want at the end. Now if we look at this one's easy. The speed of light is just a distance over a time, so meters per second. And so if we want to say get a distance out of this, we could multiply by a time, and our 2 times would cancel out, and we would get a distance as our units. So that's as simple as we need to get for the speed of light. Now for Planck's constant, this one's simpler than gravity, but it's a little more complex than the speed of light. So Planck's constant is represented by h, and like I said, it's the proportion between a elementary particle's frequency to its energy. So the units of frequency are 1 over time. So how can we think about this? Well, we know that if a wave makes 1 revolution per second, that means that its frequency is 1 hertz. So then energy, what are its units? So we can think of energy similarly to how we thought about force. So remember, our force was trying to accelerate or speed up or slow down some mass. So energy then is just a force over a distance. The way to keep this straight in my mind is using a stationary force. So if you imagine that you're stuck in between 2 concrete blocks and you're trying to push yourself apart like this. You can push as hard as you want, but these concrete blocks aren't going to move. So you're still applying some force, but there's no distance associated with it. So if our block were being sped up and we were actually changing its position, then we would be expending energy. So the units of energy are just the units of force times another distance. So that gives us md squared over t squared. So now we have our units for energy, which we use in our equation with our frequency. Where are we at now? We've got our 3 fundamental constants, c, g, and h. The speed of light, the gravitational constant, and Planck's constant. So c's units were just distance over time, or meters per second. G's units were d cubed over mt squared. It's just used to cancel out the other factors in the force of gravity equation so that we get a force out in terms of our units. And then the units of h are, we have energy on the left side, and we've said that the units of energy was just a force multiplied by a distance, md squared over t squared. So these are the units for our energy, and then that equals Planck's constant times the frequency of the elementary particle. So h here, Planck's constant, is like our Lego block. It can't be divided up anymore. So the energy is some multiple of this Lego block by the frequency of the elementary particle. So that's what it means when we say this is the quantity of energy. So if we want to find out what the units of h are, we need to do a little bit of algebra. So we've got h here, and then our frequency, which is 1 over time. The time it takes to make 1 revolution of the wave. So that gives us our frequency. So now all we have to do is multiply both sides by t, and we get the units of h, which is our next fundamental constant. So h is just md squared over t. So now we have all the units that we need in order to form a distance from 3 fundamental constants which appear in all sorts of physical phenomena and quantum equations. The specific way in which we have to combine these three constants is the square root of hg over c cubed. Now if we work this out, we'll get a unit of length. If we say, first we'll just do h times g. The units of that would be m d squared over t, g d cubed over mt squared, and then we just cancel everything out. So we have the m's cancel out, the d's add up, d to the fifth, and the t's add up, t to the 3. So then our units of c are distance over time, which is our speed, and then we raise that to the third power, hg divided by c cubed. What's that going to give us? D to the fifth over t cubed divided by d cubed. So the d's cancel and we get 2 d's on the top, d squared, and the t's cancel, so we get just distance squared. And then if we take the square root of distance squared, we get simply distance. And so that's how we combine the three fundamental constants in their units to get a final distance value.